Hi everyone. It's genuinely a great honor to share my recent work about emotion recognition with all of you. My name is Yuqing, and I'm an undergraduate student at Beihang University. I'm presenting my paper titled Emotion Recognition based on Piezoelectric Keystroke Dynamics and Machine Learning, which was done in cooperation with a fellow student and guided by mentor Gao at Beihang University. Let's begin with the research background. People rely on mobile phones nowadays. Such a tiny touch screen brings so much convenience and amazing experience to our lives. In a recent survey from Apple Company, there are more than 1 billion active iPhone users all over the world. As the technology becomes more mature, developers started to teach AI to learn our emotions and use these knowledges to better serve us. It isn't difficult to imagine, since cameras can capture our smile and tears, and microphones can record our laughs and screaming. All the traits can be indications of our emotions. But is touch, this action itself, powerful enough to discriminate emotions? The answer is yes. Compared with voice, facial expression, body movement, or physiological signal, touch is outperformed, for it doesn't need extra equipment and fit the daily scenario quite well. Let's imagine when we are typing dirty words on Twitter, a tip will pop out to convince us to calm down and think twice. When we feel upset, Siri will start to recommend funny videos and stories to help delight our mood. The future is promising. Studies show exciting results to prove that touch actions do have features which can help distinguish emotions. This technique gained neuroscience proof that emotion can impact on slight muscle activity in 2017. The accuracies of past researches are optimistic, most of which are above 70%. However, they suffer from the limitation of the requirement of long-term text input, which takes time to find the regular pattern and can't meet the requirements for timely feedback. This gap between high recognition accuracy and simple task mission is originated from the unsatisfied force touch accuracy supported by the current mainstream touch sensing product. For instance, in this literature, the authors conduct the experiment on Samsung Galaxy S2. However, currently, force levels from certain commercial smartphones accommodate just 2 levels. With the development of piezoelectric technology, which provides both high force sensing sensitivity and resolution, we see the potential to bridge the gap between short text input time and high emotion recognition accuracy, because precise force data are available now. Thus, in this article, we present an emotion recognition technique based on piezoelectric touch panel. The procedure of our research is shown in this figure. Firstly, we collect the data. Volunteers need to listen to International Affective Digitized Sounds, which is a set of music composed to induce people's specific emotions. Then they are required to input a 6-digit password, 924856, for feature collection. And at last, they fill the PAD questionnaire for emotion evaluation. For every emotion, the participants need to repeatedly enter passwords for 48 times. This experimental design has won the affirmation of psychological experts. A prototype of piezoelectric touch panel was designed to detect users' keystroke habits in different emotional states. As shown in this figure, the panel consists of 4 layers: cover layer, top electrode, piezoelectric material, which is PVDF, and ground electrode. ITO electrodes were arranged as a 4x4 matrix, where each of 16 electrodes stands for a numeral or alphabetic key during the process of password entry. In our study, 6 kinds of features are applied to represent keystroke behaviors, which are dwelling time, flying time, lifting time, recovering time, pressure value, and the acting weight of pressure. Dwelling time, flying time, and pressure value were popularly used in previous keystroke studies. Lifting time and recovering time are added for they represent the degree of energy concentration. Both pressure value and the acting weight of pressure are chosen, for the former represents the values of pressure and the latter represents the speed of the release action. After extraction, we got a 35-dimension vector. Next comes to the method of processing the 35-dimension vector. Analysis of variance, ANOVA, a typical method in statistical field, is applied to the significance test of features. P-values are given to represent the significance of difference for each feature between different emotions. A low value of P indicates a significant difference in corresponding feature between classes, which is always below 0.05. In this table, the lowest 10 p-values and corresponding features from a randomly selected volunteer were shown. It can be observed that lots of features vary prominently between classes, which reveals individual difference exists in keystroke habits under various emotion states. Then, linear discrimination analysis (LDA) is used to reduce the dimensions of vectors before model training, which aims to extract information comprehensively and reduce the computation requirements as well. A series of 3-dimension vectors were obtained after LDA. For instance, 2-dimension combination of distributions collected from a random volunteer are shown in this figure. For this volunteer, sadness and the other 3 emotions can be easily distinguished from dimension 1, and distinction between happiness and disgust can be observed according to dimension 2. However, the partly mixture of happiness and fear in dimension 2 and 3 may result in some mistakes when classified. Based on the introduced methods mentioned above, we explore how emotions affect individuals' keystroke habits. It's important to make it clear first that emotions affect individuals' keystroke habits differently. As shown in this figure, the emotions influence individuals in different ways. For instance, when experiencing the emotion of fear, volunteer 1 tends to raise the typing pressure, while volunteer 2 tends to decrease the pressure. Meanwhile, a specific dwelling time will increase when volunteer 1 undergoes side emotion. However, that same dwelling time feature won't make a significant difference when volunteer 2's emotion changes. The analysis above indicates that it is necessary to establish personalized models for emotion classification. Now let's talk about the final results of recognition accuracy. The Random Forest Classifier is applied to complete the classification, for it had better performances in multiple previous studies. The different emotions may lead to many differences in the detection accuracy and the size of error bar. Fear has the highest average detection accuracy, which is 83.09%, and the smallest error bar, which is 1.15%. That can be explained by the characteristics of fear. For example, fear has the greatest influence on people's neural and muscle activities among all the other emotions. The larger error bars of disgust and sadness compared to other emotions are caused by individual difference. Different individual is sensitive to different emotions, which leads to a fluctuation of detection accuracy towards one emotion. The error bar of total accuracy is quite small, which is 1.49%, revealing that our results are universal and can be applied to situations that only have small number of subjects. The average total accuracy is 78.31%, which is higher than previous studies. Moreover, it should be noted that our mission is simplified to just password entry, and our features are made only of time and pressure traits. In summary, a keystroke emotion detection method based on piezoelectric touch panel is presented. After fulfilling simplified missions of password entry, features from time and pressure dimensions are extracted. Finally, an average detection accuracy of 78.31% is achieved with Random Forest Classifier. In our future work, we will increase the kinds of emotions and expand the size of our data sets to make our conclusion more convincing and more practical. Thanks for your listening.